Hello everyone, I hope you all are doing well and today we are going to discuss on quantum mechanics, that is from attractive Dirac delta potential function. You know the things very well. I am going to shortly revise that. Okay, let us concentrate on the notes. Okay. As the name suggests, attractive Dirac delta, that means the potential is in the form like this. See, V of x is equal to minus alpha delta x, and here negative sign is due to the attractive in nature. Okay, and see the attractive delta potential, that is when x is not equal to 0, this side, then potential equal to 0. Okay, but when the x equal to 0, then potential tends to minus infinity. Okay, that's why this is attractive delta potential, and a spikes come when at the origin. Okay, then similarly in repulsive Dirac potential, there will be plus sign in potential. Okay, then attractive delta potential can be of two types. One is of bound state and another is of scattering state. In bound state, what happens? The energy is less than 0, that is of decaying state. Okay, and in scattering state, or if we can say it as oscillatory state, energy is greater 0. Okay, first let's see for bound state system. For bound states, see the figure. I have drawn the energy in this side, lower side. So here E is less 0, E is less 0 in region 1 and 2, and potential is 0 when x is not equal to 0 and x is equal to 0, the spikes occur. Okay, and by using the Schrodinger time independent equation, uh, that is of this form, then I get the things in region 1 and region 2 potential 0. So by applying the things, that del square psi by del x square, to make the k, I take the negative sign. So things are occur like this. This is the equation, and the solution of this equation is psi of x is equal to root k e power minus k x mod. Okay, and k is the wave number, and this is of 2m minus e divided by h cot square whole root. If I take the mod, then 2m e by h cot square. Okay, so our wave function for the attractive delta potential is of this format. See, when x tends to plus minus infinite, that means wave function vanishes. Okay, but at x equal to 0, psi of 0 is equal to root k. That means at origin there is some value of wave function. See how it is. This is the potential. So according to this, at origin the wave function is root k, and at it comes to at we comes to plus infinite to minus infinite, then wave function r is decreases exponentially like this. Okay, and then that wave function is continuous everywhere and symmetric in nature, as this is where exponential is in mod x form. Okay, but psi prime is not continuous when V is undefined. See, put uh, V is equal to minus alpha delta of x. If we put, then our Schrodinger equation is del square psi by del x square is equal to minus 2m by h cot square E plus V. I put the value of V, and not equal to 0. Okay, if I write these things, see, the second order derivative of psi is related to the delta function. Okay, that means so For a first order derivative of psi, there will be discontinuity occurs. Okay, and the amount of discontinuity is how much? That amount of discontinuity is this much. That del psi by del x in the infinitesimal change minus del psi by del x in 0 to plus infinite plus e to minus ei taken. In this limit, the discontinuity is integration of minus infinity to plus infinity minus 2m by h squared square alpha delta x psi dx. If you do the integration, you will get the amount of discontinuity. This is the important thing. Keep in mind, it comes from this Schrodinger equation. You can find it um, from this. Okay, let's go to the next. Next is k. K is the wave number, as you know, and the by some derivation we get the value of k. We keep in mind because we are doing um, formula basis things. I am not going to derivation, so keep in mind k is equal to m alpha by h squared square. Here k is the wave number and alpha is the coefficient of delta f x. See where here is the potential given and that alpha is the coefficient of Dirac delta. Okay, so k equal to m alpha by h squared square, and how we get if the other potential coefficient is given. See, we can write k equal to mass by h squared square into coefficient of delta x mod. Keep in mind, and similarly energy can be find out if alpha coefficient of delta x given, that minus m by 2 h squared square alpha of mod square. Okay, this is the important thing. Similarly, you can find out the p square average, that is the momentum equal to 2m. Put the values, you will get those values like this. Okay, see, the expectation value of p is 0 because the our wave function is a real wave function. So expectation of value of p is 0. You can find out by the average expectation formula. Okay, and the expectation of x is also 0 because of symmetric wave function in nature. Okay, and another thing, x square expectation is equal to, if you find out by this, here divided by psi star psi dx will come, but due to normalized wave function I have taken, so I did not divide it. So the value of x square expectation is 1 by 2 k square. Okay, if you put the values of k, that k is m by h squared square alpha, then you will get the value of x square expectation, that is h squared to the power 4 to m square alpha square. Okay, and see, the uncertainty values of Dirac delta, attractive Dirac delta is squared by root 2. You can find out by this. Okay, and another thing I left, that if you break the things of energy like this, you will get these values. And see, here energy is independent of n, that is the n is the values of 1 2 3 that are represent the different states. Here energy is independent of n, so there is only one bound state exists. Okay, for the Dirac potential of this form. Okay, and then, and the number of bound states we can calculate by this formula, that is n minus 1 pi by 2 less than gamma square less than equal to n pi by 2, and here gamma square is equal to 2 m v naught alpha square by h naught square. Okay, you have to keep in mind this one and this one, so that you can find out the number of bound states. And for even states, that means in 0 to 4, that means ground state, first excitated state, second excitated, like third excitated, like ground state, first excitated, second excitated. incant 0, so n will be ground state, first accepted state like this. So sorry, ground state, second accepted state like this. For n even you will get the even number of states, and for odd states you will get n odd. Okay, so n depends on the number of ground states. Then we have discussed all about bound states, and here we are going to discuss about scattering states. In scattering states, our psi will be oscillatory everywhere. That means I have taken the energy here, f of the x-axis. So is greater v. Here this is the potential. Is greater v. Is greater v. So function will be oscillatory. Okay. And in region 1 and region 2, the wave function will be a e to power I kx, b e to power. In region 1, the wave function is a e to power I kx and b e to power minus I kx. And here this term represents the incident wave function, and this term is reflected wave function in region 1, and psi 2 represents the wave function in the region 2. Here the transmitted wave function, and this is the reflected in region 2, but there is no reflection, so this term is ignored. Only psi 2 is this much. Okay, and if you want to find the amplitude, the relation between amplitude, you can use these things, b in terms of a and f in terms of a. Here beta is m alpha by h cos square k, and r is the reflection. Reflection is 1 by 1 plus delta, and delta is the 2 h cot square e by m alpha square, and t is the transmission. And is as you know the relation, transmission plus reflection is equal to 1. Okay, by this you can find out the things. And here the k is 2m e by h cot square, because here e is positive. Okay, m number. And all the things I have already mentioned, and thank you.